So this will be the last lecture in my series about random matrices and machine learning. So I have tried to cover some machine learning aspects, mathematical aspects of machine learning, but of course mostly from the perspective of random matrices. So I'm working on random matrices, so I like to see how random matrices can be applied and how machine learning can give us new ideas and problems about random matrices. Okay, so I think we have covered quite a bit. Maybe what is still at the moment not so well understood is the evolution of the learning process, how to describe this. We had the neural tangent kernel, but this is of course a first approximation and we have to go beyond this. Okay, but at the moment I cannot say more about this, so I will leave it like this. I hope I have shown you that at least for some models, toy models, or at least for some ideas to understand neural networks, random matrices are important and play a role, and that being able to calculate the eigenvalue distribution or the Stieltjes transform of such random matrices is quite important. Okay, and so today in the last lecture I want to go a little bit in this direction, namely show you that there is a quite a modern theory which allows to deal with random matrices, namely free probability theory. That's a subject I'm usually working on, which should be relevant for such things. And so I want just to give you a very high-level overview on what free probability can do, or how it can address the problems we have. Okay, and the main problems which I tried to convince you that they are relevant in the machine learning context is that we are able not only to deal with maybe with one random matrix, maybe just calculate the eigenvalue distribution of the Wishart matrices, Marchenko-Pastur, but that if we make more complicated models, then maybe we have several random matrices and we must be able to deal with complicated expressions in them, polynomials or maybe even rational functions. So the question is, can we actually deal with this in a very general setting? Of course, we looked on specific examples, but free probability theory gives you a very conceptual and general tool for dealing with this. So what I want to talk about today is free probability theory, and in particular maybe also this operator valued version, which allows you also to deal with polynomials in random matrices. So there will be two messages more or less. I mean, so there's free probability theory, which has somehow the flavor of classical probability theory, but it allows you instead to deal with classical random variables. It allows you to deal with random matrices, which are non-commuting objects, so it has a kind of non-commutative flavor. And in the same way as in classical probability theory, we can deal quite easily with the sum of independent random variables. In free probability theory, we can deal with the sum of free random variables, which corresponds to the sum of specific random matrix models. Good, but of course, we saw that it's not just the sum we are interested, but usually we have more complicated expressions in several random matrices, namely polynomials or rational functions. Okay, and the operator valued version of free probability theory actually allows to deal with this. Okay, so those are two things which I want to give you a very general idea in the following. And if you want to see more of this, I mean, I have other lectures which are also recorded where you can go more into the details of this. Okay, so let me start by telling you a little bit about random matrices, or maybe motivating somehow the structure of free probability theory from our random matrix perspective. Okay, and maybe first of all I should say free probability theory. So this was created, invented and developed mostly by Dan Voiculescu. And so this started in the 1980s, maybe 85 or 86. Were the first papers on this, and it is still an ongoing, very active subject in mathematics, and it has applications to many other fields because it has relations to random matrices. Okay, and in our context, we looked on matrices, random matrices of this Wishart type. So I had non-self-adjoint random matrices, let's say W, and then we looked on its singular values, or this means on the eigenvalues of W star. Of course, eigenvalues we can only take of self-adjoint or symmetric matrices. And maybe now I don't want to look on the Wishart type of matrices, but I want directly to look on the self-adjoint symmetric matrices, which are more of a Wigner type. Okay, so I just want, just for this motivation here, consider now matrices which are actually, let's say, symmetric. So the entries, so X is an n by n matrix, but I assume it is symmetric. So X is the same as its transpose, which means, of course, that the entries are symmetric. Xij is the same as Xji. Good. Okay, and then, of course, we consider random matrices. Classical Wigner matrices are those matrices where the entries are independent. But of course, even if we start from such matrices and we take products of several matrices of these types, we get something where the entries are not independent anymore. So the independence of the entries is usually not a property which we have for general matrices in our setting. Okay, but we have seen that even after taking maybe powers, or no, not powers, but product of two matrices, and then even entry-wise nonlinear functionals, we still have a structure of the random matrices, namely a structure of the cumulants, the classical cumulants of the entries. We saw that at least in leading order, it's only the cyclic kind of cumulants of the entries where we have a cyclic structure in the indices. All the other ones are not of the leading order, and they will, in the calculation of eigenvalue distributions, not make a contribution. Okay, good. So that's what I want to start. So typically, the random matrices we have to deal with have this special structure. And so let me recall. So in leading order, only cumulants with a kind of cyclic index structure survive. Okay, so what do I mean with this? So namely, if I'm looking on cumulants, we talked about cumulants, classical cumulants, which are determined in terms of the moments by these moment-cumulant formulas. So I denoted them by k or kappa. So let's say an else cumulant of the entry. So I have L arguments, and those arguments are entries of my matrix. So they have indices. So in principle, I could have here all possible indices, but in leading order, in the order which contributes in the final calculations, only specific indices appear. So namely, only the indices structure where, okay, so let's say for the first index, for the first entry, I have I1, I2, but then the second entry, X, must have the same index as here again. So I must have I2 and then I3, but then the next guy must repeat this I3 and then have an I4, and so on, up to the last one, which has to repeat the IL, which I had before, but then the last one has to be the same as the first one. So I mean, I have this repeating structure in this way, but also in a cyclic way, because usually if we calculate traces, then you see that we also should have a cyclic condition. I mean, this here is like matrix multiplication, that we repeat the index, the last index of one entry is the first one of the next one. So this corresponds to doing matrix multiplication. And if you also take the trace, then also the last guy should be the same as the first one. So here the last one is this I1 again. Okay, so only those guys contribute, and they are in N. So N is the size of our matrices. They go in this setting here with n to the power L minus 1. So this means the first cumulant is of order 1, the second cumulant of order 1 over n, and so on. And maybe we should remember that, of course, the entries of the cumulants, they commute. So it means that I can do some permutation of the entries here, such that after the permutation, I find the cyclic structure. Or in more general, this means this I2 here must appear somewhere again as the first index of the next x, and then the second of this next one must appear again. So I find a cycle where I can go through all the indices. Good. Okay. So that is somehow the structure of those. The relevant structure of the random matrices, which usually are showing up in our context. Okay, they have this structure, and actually the value of those cumulants is independent of the actual value of the indices, at least if all the indices are different. If some of them are the same, I mean, then okay, there are some more sub-cycle structures, and the situation is more complicated. But for the calculation of moments in the limit, the main information is given by those guys where all the i's I1 up to IL appearing here are different. Okay, so this is of this order, and their value is independent of the actual choice of I1 up to IL, which of course are all indices between 1 and n, but let me here assume or say for distinct guys like this. Okay, and then so the main quantity, the main number, which I really need in my calculation is actually the value of those guys for each L. And so maybe let me give a name to this. Maybe let me call this RL. So RL is the leading order of this cumulant, is this cyclic structure. So this means if I want to write it as a limit, it's of this order, so I should multiply it with n to the power L minus 1, and then it has a limit. That's what I'm saying here. And this limit I denote by RL. So this is, by definition, the limit, if n goes to infinity, of n to the L minus 1 times such a cyclic cumulant, I1, I2, and so on, up to XIL, I1. Good, okay, and of course I say this is the only, those are the cumulants which survive in leading order, but of course I mean for different L I have here different orders. So first order cumulant is of order 1, second cumulant is of order 1 over n, next one of 1 over n squared. So maybe you would say, okay, this means only first order cumulants should play a role in a limit. But of course you should also take into account that I have much more cumulants of this type L, of let's say of second order, than of first order, which show up in my calculation, because I have this for all i's, and if L is bigger, then I have more possibilities for the indices. Essentially, I have n to the L indices. Okay, so this leading order here, this for the L's cumulant is exactly what survives, or what survives as a contribution in the calculation of the eigenvalue distribution. So namely, let us look on this, that those cumulants here are exactly the quantities which we need for calculating the eigenvalue distribution. And of course, the eigenvalue distribution of our matrix corresponds to knowing the moments of our matrix. And the moments, of course, are given by taking the expectation of a trace of a power of our matrix. So the nth moment of our matrix is the normalized trace of the nth power of the matrix, and then I average over the randomness. And of course, so this is the expectation of 1 over n. This is the normalized trace, so this is 1 over n times the usual trace of x to the L. And then I can, of course, write the trace of x to the L in terms of the entries of my matrix. So then this is taking out the 1 over n I have now a sum over indices, namely exactly L of them, I1 up to IL, all running from 1 up to n. And here I take the expectation, and now I get exactly a product of guys like this. Now I really have matrix multiplication and a trace. So I have here xi1, i2 times xi2, i3, and so on, up to xil, I1. Okay, so summing over this I2 is the product of this matrix with this, and summing over I3 is multiplying the next matrix, and then I'm summing over I1 is really taking the trace of this power. Yeah, okay, and now we know that, I mean, here I have the expectation of the product of the matrix entries, and here, of course, I have made assumptions, or I observe a property of the cumulants, so I should rewrite this in terms of cumulants, and we have the moment-cumulant formula, which tells us that such an expectation is given by summing over all partitions of L points, and then I get a contribution for each of them, which is a classical cumulant indexed by this pi of the x's which I have here, xi1, i2, and so on up to xi L I1. Okay, and if pi is now the largest partition, which means all indices are taken together, then here I have exactly a cumulant like this. Okay, but then of course I get subleading order contributions, and one has to see that actually, what are the leading order contributions which survive. And maybe if you just think about, maybe first think about if I have here the 1n, so if I take here the 1n, then this here gives me exactly this cumulant here, which goes then with n to the minus L minus 1. Here I have another 1 over n. So this quantity here with the 1 over n there goes like 1 divided by n to the L. Okay, but now we are summing over all i's, and it's enough to sum over the ones for which the i's are distinct, so that I really have this. The other ones, okay, will not make a contribution here. And so you see, I have here a sum over n to the L, the order n to the n number of terms, and each term is of the order 1 over n to the L, so the whole thing together is in order 1. So this means this here really makes a contribution in order 1. And the other pi's one has to think about also have the same kind of order. So this means this here really is the contribution, or the asymptotics of the cumulants, which in the end is responsible that in the calculations asymptotically we get a finite result. Okay, and you also see that of course here the scaling should be really like this. So first order cumulant should be of order 1, a second order cumulant of the entries should be of order 1 over n, a third order cumulant of the entries should be of order 1 over n squared, and so on. Good, okay, so this is all nice, but question is, can we get some more structure out of this? So I mean, I have here written down the beginning of a calculation, namely calculating the else moment of my matrix, writing it down in terms of the entries. For the entries, we have some information about the cumulants, and the main information are just those guys RL here. So in principle, you see what I get here should be something like a sum over partitions, and then I get contributions from the R's. And the question is, can we all sort this out in a nice and useful and clean way? And actually, this is possible. And in the end, we get a kind of moment-cumulant formula, but it's a kind of non-commutative one, or maybe a free moment-cumulant formula. Namely, we will see that we get essentially contributions here in terms of the R's, but not all pi's contribute. So it will be only specific ones. And maybe we should look on some examples to see this in a clear way. Maybe let's first do the smallest one. Yeah, so namely L equal to 1. So what is this calculation here doing in this case? So I want to take the expectation of the trace of x, or actually I want to take it asymptotically. So x is an n by n matrix, which if n goes to infinity behaves like this, and then I want to look what is asymptotically its first moment. And of course in this case, this here is just 1 over n. Then I have just one index to sum over, so I is running from 1 up to n, and then I have the expectation, and here I just have xii. I mean, taking the trace of my matrix is just summing over the diagonal. Yeah, okay, and here this expectation of this is the same as the first cumulant of xii. Yeah, and the first cumulant in our matrix ensembles here is of order 1. So actually this here asymptotically behaves like R1. Okay, so all those guys are 1. I sum over them n times, but I'm also dividing by 1 over n. So this means this here really just gives me an R1. I just see the contribution of the first cumulant of my entry on the diagonal, which of course is the same as the moment on the diagonal. Okay, this is first moment is first R1. This is not too surprising. Good, so for L equal to 2, if I take the expectation of the trace of x squared, what do I get there? Then of course I have to sum over two i's. Let me call them now I and j, instead I1 and I2. So I have the sum over I and j, each running from 1 up to n. I have this 1 over n factor coming from the normalization of the trace, and then I have the expectation of xij, xji. So this is matrix product between the two x's, and summing over the I is taking the trace. Okay, and now again I write this expectation here in terms of the cumulants of the entries, and the second moment is summing over all pairings of two elements. There are two of them, so I get the contribution the contributions which I get are exactly those two. I have here an x, I have here an x. Okay, I combine them together, which gives me a second cumulant with the entry xij, comma xji, plus this term here gives me a product of first order cumulants, so it's k1 of xij times k1 of xji. Okay, and now we see this contribution here, I and j. For this contribution we can restrict to the case where I and j are different, because if they are the same, they will not survive in the sum. So if I and j are different, this is of order 1 over n, or this is always of order 1 over n. But if I and j are different, it's always the same value. So this here behaves like 1 over n times R2. R2 is the leading order of this guy in this asymptotic. And again, you see this is nice, this fits. I have a 1 over n, another 1 over n, so I have 1 over n squared, but I'm summing over I and j. Okay, they are different, so but nevertheless I'm summing. The order is n squared of the number of terms which I sum over. So I have n squared times 1 over n squared, so this will go away, and this here in the limit just gives me R2. Okay, but here's another contribution. So do we get something from this? And of course here, so we have here k1s, and now we might get worried because the k1s are of order 1. Okay, so I have here something which is of order 1, and here something which is of order 1. And then the contribution would be R1, and here it would be R1. But we also have to see that we need the cyclicity, and the cyclicity for the first, if I only have one argument, means of course the arguments should be the same. So I get here something of order 1 if I is equal to j. Otherwise it's lower order which is not there. So here I get actually a delta ij, and here I get a delta ij. Which means I get here terms of order 1, namely R1 times R1, but only in the case when I is equal to j. So actually, I don't have n squared terms for which I get this contribution, but only n terms, and each of them has this factor 1 over n. So again, altogether, I'm in leading order. And this here together gives then R1 times R1. And so what we get here in the limit is that this here converges to R2 plus R1 times R1. Okay, now you see, or you say, okay, what I get here is just the ordinary moment-cumulant formula. I'm expressing the moments of my matrices in terms of these R's, and this formula is like for the cumulant. So it looks as if these R's would now just be the cumulants of the distribution of the matrix. Okay, so this is true for these two guys. For third order, it will also be true, but then for higher orders, the non-commutativity is going to play a role, and we will see that we still get a formula of this type, but the actual concrete form, namely which pi's make a contribution, this will change. And for this, let us look on maybe the fourth order, because there we will see for the first time a difference. So let us now look on the case L equal to 4, so the fourth moment of my matrix. And to make life easier, so that I don't have too many contributing terms, let me assume that, let's say that R1 and R3 is equal to 0. So if I have kind of even distributions, then this will happen. So this is just to simplify life a bit. Okay, so I consider L equal to 4. And I assume that R1 is equal to 0, maybe also R3, but R1 actually would be enough. Okay, and I want now to calculate the fourth moment of my matrix. And yeah, so what is this? Yeah, by the general formula, of course, this is just 1 over n. Then I have to sum over I1 up to I4, so I have 4i indices, running from 1 up to n, and I have the expectation of, I have x I1, I2, comma, x I2, I3, comma, x I3, I4, comma, x I4, and then going back to the first one, I1. Okay, summing over all this. Matrix multiplication, here, here, and here, and taking the trace is here. Yeah, and now, of course, again, I write this in terms as a sum over cumulants, as a sum over partitions. Each partition makes a contribution, which is given in terms of the cumulants, essentially by taking the product of a cumulant for each block. And because I have assumed that R1 and R3 are equal to 0, the only possibilities which make a contribution are the ones for which I have only a block of size 4, or the ones where I have 2 blocks of size 2. The situations where I have blocks of size 1, they will disappear, they are 0. So this here, actually, under this assumption, is the same as the cumulant of order 4 plus, and then I have 3 terms. I have 3 partitions where I have 2 blocks of size 2. So namely 1 and 2, 2 and 3 is together, 1 and 4, 2 and 3 is together, or 1 and 3 and 2 and 4 are together. Okay, and yeah, in the classical world, those, this gives something. Those would give the same contribution, but now we have to see that actually here the situation is different. But let us first look on kappa 4. So kappa 4, so what is this? This is just taking the cumulant, and actually here I have the product, so here I don't have commas. I don't have to. So here I have the product of those guys, if I take the expectation. If I take the cumulant, I'm putting commas there, and I have my 4 arguments. And then, of course, I have here just this cyclic structure, which in our models always goes like R4 times n to the minus 3 in this case, if all the i's are different. But That's, we can assume. So what we have here, this goes like R4 times n to the minus 3. This 1 over n here makes this to n to the minus 4, but then we are summing over n to the 4 order of terms. So we have n to the 4 terms, which are of order 1 over n fourth. So this in the limit goes to 1. And so what we get from here is the R4. So we just get essentially this guy here. Yeah, but how about the other ones? So how is it now about this product? We should look on this product. So this is a product of two second order cumulants, one for this block and one for this block. The entry of the first kappa are the first two arguments, so x I1, I2, comma, x I2, I3. And then times the second order cumulant of the last two arguments, which is xi3, I4, comma, xi4, I1. Yeah, okay, so those are second order cumulants, so they go like 1 over n. So each of them goes like 1 over n, 1 over n. And then, of course, it's R2, and here the same, 1 over n, R2. Okay, and now again we have the same apparently the same problem as before, namely I have 1 over m, which is 1 over n squared, together with this extra 1 over m, n from the normalization of the trace, it's 1 over n to the 3. So if I would have now all my indices which make this contribution, this would be a problem and things would explode. But again, of course, not all indices make you this contribution, because I need the cyclicity in the indices. And cyclicity here means that this here must be the same as this. I mean, here it is okay, but here, I mean, the whole cycle continues here. But now the cycle is broken, and I need a subcycle here, which means I3 must be equal to I1. So this only makes a contribution if I1 is equal to I3. And here, what is here? Here I also need the cyclicity. So here this must be equal to this, but this is the same condition as here. So it's still the same condition that I3 must be equal to I1. So this means in my summation over I1, I2, I3 and I4, only 3 of them can be chosen independently, and I3 must be equal to I1. So I'm only summing in the order of n to the power 3 number of terms, and then each of them gives a 1 over n to the power 3, means altogether they contribute of order 1. And what do they contribute? They contribute R2 times R2. So this thing here makes in the limit the contribution R2 times R2, which is again what we would expect. Okay, so this still looks like the classical cumulant formula. If we do this here, I mean this will do the same. So this here will also make the contribution R2, R2, and now only the last one will be different. Okay, and yeah, maybe I already mentioned it. Free probability is like classical probability, but the non-commutativity makes an extra contribution, or has an extra flavor, namely it doesn't like crossings. Okay, so this is a crossing partition compared to those. I mean, I won't define crossing explicitly, precisely, but I hope you see if I draw those pictures of my partitions. I mean, this here has a crossing between those two blocks, where the others don't. I mean, those those two don't have a crossing between their two blocks. Okay, and this here is different. So namely, let us look what is the contribution of this. So this guy here. So I mean, this is still a product of two second order cumulants, one for each of the blocks. So I have a kappa 2 of the arguments which are sitting here and here. And so here I have x I1, I2. But here I'm now at this guy here. So I have x I3, I4. So I'm taking this partition now of the 4 arguments, and so you see, I mean, I have take this and this as the 2 arguments of the first cumulant, and this as the argument of the second. So here, for the second, I get a second order cumulant of xi2, i3, comma, x i4, i1. Okay, and now you see that again, in principle, those are second order cumulants, so they make a contribution R2 times 1 over n, but then of course only if the indices have this cyclic structure. And now you see we have the cyclic structure, we have it much more destroyed than in the other cases. So I mean, what we need is essentially that this guy here is the same as this guy. Because we have symmetric matrices, I mean, you always have the possibility that this is equal to this, or this is equal, and this is equal to this, or the other way around, because xij is the same as xji. So this makes the arguments a little bit complicated. But in any case, I mean, what we need here would be that either, let's say, I1 is equal to I3, and I2 is equal to I4, or I mean, it could also be the other possibility, which would still give a cyclic structure, that I1 is equal to I4, I1 is equal to I4 plus, and then I2 must be equal to I3. Okay, and here, similarly, I mean, here we would have that I2 is equal to I4 plus I3 is equal to I1, or the other way around, that I2 is equal to I1 and I3 is equal to I4. Okay, but I mean, in any case, if you think about those possibilities, you will see that we have now to identify more indices. It's not that we can just say, okay, two indices are the same, and we still have three indices which we can choose freely, but at least two of them have to be identified according to this. I mean, you can take all combinations of this, and so you see what I have here is a delta where at least two indices are the same. Must be equal. Okay, and so this means I get a contribution R2 times 1 over n, R2 times 1 over n, so this is of order 1 over n squared, an extra 1 over n from the trace, so I have a 1 over n to the 3 as before, but then the question is how many indices can I sum over, and there are at most two independent ones, so I have at most order n squared. I have n squared, but I divide by n to the power 3, so this goes like 1 over n, or maybe even, depending which of the situations here I have, 1 over n squared to 0. So this means this contribution here in the limit goes to 0. So you see, in principle, we get a formula for the calculation of the moment of the matrix, where we are summing over partitions, and for those we get contributions, which are like in the moment-cumulant formula, namely we get 1r for each block, and we multiply them, but it's not that all partitions are now treated on the same level. I mean, some are special, some are better than the others, some are bad partitions, and they disappear at the limit. Okay, and what survives in this case are only those three contributions, but not this one. So this will go away. And this is true in general. So if we do the higher order calculations, it's actually always the crossing ones which go away. So this means in the limit, we get for the calculation of the moments of our matrix, we can express this in terms of the R's by a moment-cumulant formula, which has the same structure as the classical moment-cumulant formula, but it's not that we sum over all partitions, but we only sum over the non-crossing ones. So in general, crossing partitions will disappear in these classical moment-cumulant formulas, and what we get for the calculation of the moments of our matrices is a non-commutative projection, in some sense, of the classical moment-cumulant formula, where under this projection all the crossing partitions have disappeared and we are only left with the non-crossing ones. So what we get here is a free moment-cumulant relation between the moments of our matrices. So let's say let's say, the normalized trace of x to the L in the limit n going to infinity. Yeah, and of course taking the expectation of this. So this is the nth moment, let's say, this is ML, the nth moment of the eigenvalue of the asymptotic eigenvalue distribution of our matrix X. So this is given by a kind of free moment-cumulant relation where I'm summing over pi, but now I'm only summing over non-crossing partitions. So these NC of L are non-crossing partitions, not all partitions, and the contribution which they make is exactly the same as they do in a classical moment-cumulant formula, namely it's R pi. So this means this is the product of R's, one factor for each block of pi, and the index which I have at the R is just the size of this block. So I mean here I get just R2 times R2. Here I get R4, and for example, for something like this, I would get R2, R1, R1. Block of size 2 gives an R2, a block of size 1 gives an R1, and a block of size 1 gives another R1. So it's exactly the same. So it's this formula. So this is the free moment-cumulant formula, and the R's which show up in this context here, they are kind of cumulants, but not the classical one, but they are the cumulants in this free probability theory, so the R's are called free cumulants. Yeah, okay, and then as in the classical setting, the full power of this cumulant calculation, or the concept of cumulant, shows up if we do the multivariate situation. And there we have the same moment-cumulant formula. We can take joint moments of our random variables, and correspondingly we have joint cumulants. Okay, and the reason why the cumulants, maybe the main reason why the classical cumulants are so important, is because they characterize independence by this property of vanishing of mixed cumulants, which is very useful for many applications. Okay, and we can see here that we get the same kind of property for these R's. So namely, if we here I have defined the R only for one random matrix model, but now of course I can take several random matrices, and let's say they still have this joint. Each of them has this joint property, this property that only the cyclic structure is there. And then if I look on the joint cumulants in them, if I take them as independent, which means the entries of one matrix are independent from the entries of the other matrix, then the classical mixed cumulants vanish, which means the corresponding R's also vanish, because then there is no leading order contribution. Okay, so we see, if we go via random matrices, that because the classical mixed cumulants of entries of two independent matrices vanish. So this is the property that classical cumulants characterize independence via the vanishing of the mixed cumulants. This means that the corresponding mixed free cumulants vanish, because the free cumulants in this context are defined by taking the leading order of the cumulants, the mixed cumulants of the corresponding matrix models. Okay, so this means in this setting that the corresponding mixed free cumulants vanish. Okay, and then this means I'm here in a situation where in the limit I have two limiting objects, which are described by the property that their mixed free cumulants vanish. And this property, in analogy to classical independence, is called free independence. So we have here a situation where I have two non-commutative random variables whose free cumulants, whose mixed free cumulants vanish, and this we can take, if we like, as a definition of the notion of free independence or freeness. So this here, which is given in the limit of such independent random matrices. So this situation, this is called free independence. Or maybe just freeness. And that's the crucial notion which was introduced by Voiculescu, and which is the main concept in free probability theory. So free probability theory is a theory dealing with random variables, non-commutative random variables, where you have moments, and then you can also define free cumulants, and you have this notion of free independence, which you can here characterize by the vanishing of mixed cumulants, or we can define it here. And then you can develop a whole theory for this, and you have many things which are in parallel to the classical situation. So this here is free probability theory dealing with this here. Yeah, okay. And of course, we can now say, yeah, if we have now this vanishing of mixed cumulants, in particular, if I'm taking the sum of two free variables, this means that the cumulants are additive. Because, I mean, the cumulants are a multilinear object. So if I take the cumulants of a sum, it gives a sum of all types of mixed cumulants. There's one term which has as entry just the one variable. There's one which has as entry just the other variable. Those are the cumulants of the two variables I consider. And then there are many terms which have some arguments are the first variable, some arguments are the other one, but because they are free or freely independent, all those guys vanish. So this means the cumulants of free random variables are additive. The free cumulants of free random variables are additive in the same way as the classical cumulants of classically independent random variables are additive. And of course this gives you the possibility of calculating the sum of independent variables. In a classical setting, maybe you have the Fourier transform, which you can use. And in the free probability theory, we have a similar machinery which depends on the notion of free cumulants. Okay, so this means dealing with the sum, which corresponds to taking the convolution, classical context, the classical convolution, in the free context, the free convolution. So taking the sum of free variables, which corresponds to taking the sum of independent random matrices in the limit, this is something which we can deal with quite effectively in free probability theory. Yeah, okay, but of course, now the problem is we have seen, or the problem, I mean, we would like to do more. So, because in our machine learning context, also we have seen that we have as input, I mean, we might have matrices which are all independent, so they are all free. But then we calculate something which does not only depend on the sum of those matrices, but it depends on a mixture of products and maybe even taking rational functions or other things. So in the end, it depends on taking complicated, or depending on the model. In principle, we would like to understand polynomials in our random matrices. Okay, and so the question is, can we go over from the sum to polynomials? And in the usual, I mean, in free probability theory, that's not what can be easily done, but actually there is this operator valued version of free probability theory where we really can address this problem. And so that's the last thing, or the last message which I want to send to you, that actually we cannot only deal with the sum of free variables, which corresponds to the sum of random matrices, but we can also deal with polynomial or even rational functions in free random variables, which corresponds to, we are able to calculate the asymptotic eigenvalue distribution of polynomials of independent random matrices in our setting. Okay, and so I want to say a few words in the following about this, how this can be done again on a very high level. Just give the main idea how we really can make this transition from that we actually only know linear stuff, how we can use this for dealing with polynomial stuff. So how can we deal with a polynomial, let's say in 3 variables? And the idea is that we should reformulate a polynomial which is a nonlinear problem. We should reformulate this as a linear problem. Of course, we cannot do this in this direct way, but what we can do is we can reformulate it as a linear problem if we allow matrix coefficients. So I mean, we go over from let's say a scalar valued nonlinear problem to an operator valued linear problem. And linear problems we can deal with, even if they are operator valued. That's operator valued free probability theory, which allows us to do a kind of operator valued free convolution. So that can be done. But the main step is actually to linearize, in some sense, a nonlinear problem. And that's what I want to talk about in the following. And this is actually a very general procedure, which is not at the moment, at the beginning, not really related with free probability or freeness. So maybe this is just a very general, and maybe I just want to give you an example. So for example, assume I have 2 variables which are free, or maybe you can think of I have 2 random matrices which are independent, and I want to understand them in a limit. And what I want really to understand is a polynomial of them. And to be concrete, let me take xy plus yx plus x squared. So this is a quadratic polynomial. So I mean, what I can do essentially are sums. But I mean, even if x and y are free, I mean, those 3 guys are not free anymore. So I cannot just take the usual convolution. Good, but okay, so what do we want in order to calculate the eigenvalue distribution, or the distribution of this? We in principle want their Stieltjes transform. The Stieltjes transform is really the tool which, if we have it, we can calculate the eigenvalue distribution. So what is the Stieltjes transform of this polynomial? So P is my polynomial. Stieltjes transform depends on a complex variable set. And this is by definition the expectation of the normalized trace of my polynomial. So maybe I just denote this by P. So it's a trace of P minus z times the identity to the -1, taking the trace and the expectation. And so that's what I really have to calculate somehow. Okay, and now I say, this is a polynomial problem, and we cannot really reduce it to linear things. I mean, we cannot factorize this, for example, in linear terms, because there is no way of doing this in a meaningful way. And so how can we calculate the inverse of this without and relate this with a kind of linear problem? Good, and the idea is that I should embed this problem into matrix problems. So I should lift this problem, which is a problem on, let's say, a scalar valued level, so just an ordinary level, but I embed this in a priori more complicated situation where I embed it into matrices, and then in the matrices I have possibilities for doing factorizations or into linear terms, which on this level cannot be done. Okay, so this sounds crazy, but in the end this is very easy and very helpful. So namely, what am I doing? So I mean what I really want is the inverse of this guy here. Okay, and so my guy is xy, let's say, plus yx minus z times the identity. I want to take the inverse of this, but directly I don't know what to do, so I embed this into a 3x3 matrix where I just add here quite trivial things. So namely here I'm adding a -1, 0, 2x2 matrix. Okay, and I mean this matrix is invertible, so the whole matrix here is invertible exactly if this guy here is invertible. So the invertibility question has now lifted into the matrices, but it's still, in the end, it's the invertibility of this guy here. So can I invert this, and can I also calculate the inverse of this? I'm embedding this in these 3 by 3 matrices, and why am I doing this? Because here I can now factorize this into a non-trivial way. So namely, this can be written as 1, then I have here y plus x over 2, x 0, 1, 0, 1, right, e, and x was 2, x 0, 1, 1, 2, 1, 0, 0, I plus 2, is 1. So this is a factorization, and it's easy to check that this is true. So I mean, how do I get this guy here? So I get this guy here by multiplying. Okay, I can multiply this times this times this, so this gives me the minus z here. Then I can also multiply this with this times this. And this gives me a y times x plus x squared over 2. So this is, I'm missing here the x squared, plus x squared minus z times z entity. So x squared is part of my p. So half of this I'm getting also from here. And then I can also multiply this, which gives me the xy and the other half of this guy. Okay, and the rest is just going away more or less. So you should check it for yourself. This is just an easy, very easy calculation. Maybe the point is, of course, how do I find this? Why is this the case? Yeah, I mean, they are really I mean, okay, we know that it can be done. And this looks here very special. Maybe you think, oh, this is for this very special polynomial, but actually this can be done for any polynomial. And there are algorithmic ways for doing this. So it's really clear how you should do it. There are algorithms. But I'm not going into this. It's just that there exists such a decomposition, which is very easy. And now, good. Is it useful? That's the other question. So why I'm doing this? And one point is that actually you see that now the entries which I have here in all those matrices, they are just linear in x and y. That's what I really want. I mean, I want to go back to linear problems where x and y are only showing up in a linear way. Here they are in a quadratic way where I don't know how to deal with this. But here I have factorized it into terms where they are showing up in linear ways. Okay, but I have factorized it into a product of 3 terms. If I want to take the inverse, then of course it depends on the inverse of all those guys. But now you should notice that the structure of the first and the last matrix actually is very special. Namely, they are triangular. So I have here ones here and I have something there. And such a matrix is always invertible. I mean, the inverse of such a matrix essentially is the same matrix where I have here a little bit changed here, but because I have ones here and zeros here, this is invertible. And here the same. Here it is the other way around. But such matrices are always invertible, so this means the invertibility of this guy, which is the invertibility of the polynomial in which I'm interested, is really just a question about the invertibility of this middle guy here. And actually, we can somehow calculate the inverse. I mean, I just take the inverse of this. So maybe, so let me take the inverse of this. And this, of course, this is very simple. I mean, the inverse of this guy is itself, and this inverse of this is exactly what I want. So what I get here is p minus z times the identity, the inverse, and then 0, 0, 0, 0. And the inverse of this 2 by 2 matrix is just itself. So the inverse of this is just this guy. And this guy contains what I'm interested in as a 1, 1 entry. Good. What do I get on the other side? I take the inverse of these 3 matrices. So this is then the inverse changes the order. So it's the inverse of this times the inverse of this times the inverse of this. Yeah, so the inverse of this So this is this here is the inverse of this, and if I take the inverse of such a guy, this reproduces essentially itself. So this just has ones on the diagonal, and then it has something here which is just a modification of this here, but it still has zeros there. Okay, then I should take the inverse of this guy here, which is of course complicated, times the inverse of this, and this is again something which has ones on the diagonal, and it preserves the structure. There's something here, but zeros here. Yeah, okay, and so now you see that actually what I get here, the 1, 1 entry of this matrix, that's what interests me, is given as the 1, 1 entry of this product of the three matrices, but because I have the zeros here and the zeros here, the 1, 1 entry in this guy here is just this 1 times the 1, 1 entry of this guy times this 1. So this means what I really want, namely the inverse corresponding to my polynomial, is actually the 1, 1 entry of this matrix here. Yeah, okay, and so maybe this matrix I can write down again. So what I get is P minus Z times the identity minus 1, the 1, 1 entry here. This is the 1, 1 entry of this guy here, and this guy, let me write it down again. Maybe I can again separate the set off, because you see I have here polynomial minus set. So this is the Stieltjes transform of this P, and here I also have something. I have some matrix, and then I have this extra set. So maybe it's good to also write it in this form. So I have here 0, so I have 0, x, y plus x over 2, x 0 minus 1, y plus x over 2 minus 1, 0. So this that's this matrix with the exception of this minus set. And this minus set I'm writing here in an extra matrix. Set 0, 0, 0, 0, 0, 0, 0, 0. Okay, and then I have to take the inverse of this. So that's the inverse of this, but then I only need the 1, 1 entry, or the 1, 1 entry on this side is exactly the 1, 1 entry of this whole product, but this is the 1, 1 entry of this guy. So this is here the 1, 1 entry of this whole matrix. Yeah, so this here means the 1, 1 entry of this 3 by 3 matrix. Yeah, okay, and this here now has again somehow the structure of a Stieltjes transform, but maybe in 3 by 3 matrices of this guy here, and this here is now somehow the version of my argument set. Now it's something in the 3 by 3 matrices. But so what I have in the end is really that P minus Z times the identity to the minus 1 is a matrix, and maybe I call this here P hat. This is somehow my operator valued linear version of the P, so I call this P hat, and I'm subtracting some kind of argument, this matrix here, maybe I call this lambda of Z, and I have to take the inverse of this, which is a 3 by 3 matrix, and of this I take the 1, 1 entry. Yeah, okay, and the point is now that, so I, instead of calculating this kind of Stieltjes transform of my P, I can also calculate or try to calculate this kind of Stieltjes transform in 3 by 3 matrices of this P hat. Okay, so why should P hat be better than P? I mean, this is actually lives in matrices, but this guy is something which is linear in x and y. So namely this P hat is actually a linear polynomial in x and y, but in 3 by 3 matrices, which means I can write it as a linear polynomial which has matrix coefficients. So the P hat is a linear or linear means all with a fine here, so constants are also allowed. A linear polynomial in x and y. But of course I have to pay a price. I mean, this was non-linear, this is linear, okay, but this was scalar valued, no matrices were involved in this, but this here is on a scalar valued level. So this has matrix coefficients. Yeah, and maybe let me write this explicitly. So the p hat, I'm just separating the x's and the y's and the constant terms. So I have a constant term, which is just a constant 3 by 3 matrix. So that's just the minus 1s there. So this is 0, 0, 0, 0, 0, minus 1, 0, minus 1, 0. Okay, so let's say times the identity. Then I have a contribution where I have the x's. So now I just collect the x's in this p hat. So I have here 0, 1, 1 half, 1, and I'm taking out the x to make it more explicit, times x. So this means I'm just multiplying x entry-wise. So I have an x, x over 2, x, x over 2. That's the contribution which I have there in the p hat. And then I also have the y's. So I have the y's. Where are the y's? The y's are sitting there in the corner. So here and here. Yeah, everything else is 0. So y here and a y here. So now you see this p hat really is a linear polynomial in x and y, whereas the p was quadratic. Yeah, and of course the point is now that we can deal with such linear guys even if they have matrix coefficients. So if I have now x and y which are free, then those guys here are also free in this operator valued sense. And then in this operator valued theory, we also have all the machinery for dealing with this sum of free variables. So I mean, the message is just that we can deal with this kind of problems in this operator valued setting. Okay, I mean, of course, the details are more complicated and not so easy, but in the end, it really can be done. We have the machinery for addressing such problems. And the point is that we can reformulate polynomial, non-linear problems into linear problems, but the price we have to pay is that we have to allow matrices as coefficients. But the good news is free probability has a more general version, operator valued free probability, which allows to deal with such sums. Okay, and then maybe I also mentioned rational functions. So maybe at some points it's really rational functions which we want to deal with or which we need for calculating something in our machine learning context. And actually this linearization also works for rational functions. So we can also linearize rational functions. Good. Yeah, I think that was now all I wanted to say. I mean, this was here very vague and general. So I mean, maybe the only message you should keep maybe from this lecture here is that we have free probability, which allows to deal with sums of free variables, and free variables are the limits of independent random matrix models. And then we have this extension operator valued free probability, which allows even to deal with polynomials in independent random variables, or polynomials in free variables, which corresponds to the limits of polynomials in independent random matrices. Okay, so I just wanted to say free probability theory has tools for dealing with problems which show up, at least in some models in machine learning, and which might be relevant also for other calculations in machine learning. Good. Okay, so I think I will stop here. That's the end of the whole lecture series. As I said before, I tried to give some statements, some interesting facts which are of mathematical nature, which are mathematically clear about machine learning. of course, maybe the most interesting facts and questions about machine learning and deep learning are the ones which at the moment we don't really understand so well. At least we don't really have a good mathematical theory for them, or precise, nice mathematical statements. So in particular, the evolution of the learning process is such a thing. And at the moment, I cannot really say more about this. So maybe in a few years, maybe there will be more on this. Maybe I also have understood more, and then maybe I'm coming back with another lecture series on such new exciting developments in a couple of years. But I think for now I have said everything which I can say. Okay, thank you.